Good morning. Welcome to today's Swan Analytical webinar, Engineered Systems, Sample Conditioning, What, Why, and How. Our presenter today will be Kevin Murphy. Kevin has over 25 years experience in the water industry. Prior to that, he was a member of our Army, serving multiple deployments overseas. He'll share some of his expertise and experience in the water industry. But before we get started, I want to take you through the software that we're using today. And on our next slide, you get to see how our GoToWebinar panel will help you interact with us. Right now, everyone attending is in muted mode to help minimize distractions. If you're having trouble hearing me, you may want to look at the audio options. You can either use computer audio or call in separately. If you'd like to maximize our webinar presentation and minimize the toolbar, you can do that by clicking the orange arrow in the upper left-hand corner. I did mention that you're muted, but we do want to hear from you. We'd ask you to submit your questions via the questions panel in the GoToWebinar control panel, and we're going to pull those all together and address them at the end of today's session. So with that, we'll move on to our webinar. Take it away, Kevin.
Thank you, Don. Welcome, everybody. Appreciate you showing up for the webinar today. And we'll get started here. So, steam and water sampling. Why do we sample? Basically, it's so that we can monitor the water chemistry and make sure that we can make the adjustments in the treatment needed to keep the water chemistry within the acceptable limits. So we can maintain the heat transfer efficiency and maximize it. Also, so that we can maximize the time between our chemical cleanings. Also, we want to ensure that we maximize the boiler life and the turbine life while minimizing operating and maintenance costs. Also, we want to ensure that we have the accuracy of the analysis and that we are able to do that repetitively so that we can provide the data needed to control the process. So when we design a system, we look for some of the basics of what do we need to know in order to design the system appropriately. The first thing we look at is, what is the system design? Is it a traditional drum boiler? Is it a heat recovery steam generator? Is the plant a supercritical operation? Or is it an industrial plant? Each one lends itself to specific design criteria in the conditioning of the samples. So, we also want to look at what are the subject constituents? What parameters are of interest for the application? Are we looking for sodium or silica, pH, conductivity, chlorine or turbidity, or are we looking for the verification of disinfectant? What is the chemical treatment that we're operating under? Is it an all volatile treatment with reduction agents, or is it an all volatile treatment oxidation, or is it a disinfectant system? That way we can look at how do we attack or ensure that we're looking at the specific potential problems that are in the system, whether it's flow accelerated corrosion, stress corrosion cracking, iron transport, or steam carryover.
So Kevin, I'd like to take a quick break right here and poll our audience on some of the reasons they might be attending today. We'd like to ask you, what are your biggest concerns when selecting sample conditioning equipment? Got a multiple choice here. We'll wait for some folks to click in. And you can just click any of those answers and hit enter, and we'll get the results. A lot of feedback coming in here. Still collecting responses. We'll keep it open for maybe another 5 or 10 seconds. Okay. All right, we're going to close the poll right now, and I'll share the results with you. As you can see, accuracy seems to be the biggest concern, but there's also an awful lot of folks that are looking to prevent damage to analyzers and equipment. And so Kevin, as we go along, I appreciate if you could keep that in mind and address those concerns in your presentation. And I think folks will be pretty happy on what we present here. Okay,
No problem at all. All righty. Hopefully we'll address all of those concerns as we move forward here. So we're going to take a look here at steam samples, saturated or superheated. Some of the things that we would look for or design into the conditioning solution would be, do we need isokinetic sampling? In other words, are we going to use isokinetic nozzles to pull the steam in a representative manner from the process line? What are the sample velocities? We want to go ahead and transmit that steam at the same velocities that the steam is actually processing through the system at. The velocity should be suitable to ensure that we have turbulent flow, so that when we're transporting it, the particulate and ionic components that are in the solution remain in the solution. Again, the idea is that we need to get a representative sample to bring to the analyzers so we can actually see what's happening in the process. For low pressure or low to mid temperature samples, in certain low pressure sample requirements, we don't have a whole lot of pressure to work with. So we need to design a solution that has a low enough pressure drop that we can still have enough pressure to feed the analyzers appropriately so we can get repetitive results. For low temperature samples, we may still require conditioning for the pressure reduction or flow control side, even though the temperatures are acceptable for the analysis. With that, Swan can provide conditioning for a wide variety of applications. The picture at the bottom here is actually of a distribution monitor, but you can see on the left-hand side, we actually are doing conditioning, even though this is an application where the temperatures are appropriate for the instruments, but we still need to drop pressure and control the flow to the analyzers to make sure that we're getting consistent repetitive results. Some of the important sample conditioning parameters. EPRI is one of the sources that we use in our determination of how do we approach conditioning, and the primary objective of any sampling system is to transport and condition that sample without altering the characteristics of interest. We need to get correct measurements of what's actually happening in the process without making changes to that condition when we're bringing it to the analyzer. The system parameters that we need to control in order to do that are temperature, for number one, the pressure of the sample, and the velocity or flow rate from the sample. As you can see here, with temperature, the reason why we're concerned is actually several points, but if we look at a sodium analyzer here, you can see that the maximum temperature that analyzer can operate at is 113 degrees Fahrenheit. If we look at what a traditional drum boiler operates at, 680 degrees Fahrenheit would be typical. that is not going to work bringing that sample directly to the analyzer. If we look at the pressure, again, the same instrument can handle about 20 pounds of inlet pressure, but the actual drum is operating at upwards of 2,400 PSI. Again, this is necessary for us to control the pressure as well as the temperature. And flow rate. The sodium analyzer needs a continuous, maintainable 100 milliliters per minute flow rate. But if we look at the drum boiler and the fluid movement through that, we're actually at 3 million pounds per hour, considerably more than what we would want to put through the sodium analyzer.
So we're going to stop for another quick poll here and just get the feedback from our attendees today on what sample issues will require sample conditioning. And people are clicking in. Keep it open for a little bit here. Got about a third of the audience responding so far. I'd like to hear from as many of you as we can. So far, I'm liking the responses I see. Okay, we've got about of the attendees voting now. We'll keep it open for just a couple more seconds. And we'll shut her down right now. Share those results with you. What do you think, Kevin?
I can't see the results, Tom.
My apologies. Oh, well, we've got 87% that answered all of the above, 9% flow and 4% temperature, 0% on pressure, but the winner there seems to be all of the above.
Good, good. That's what I was hoping for.
So Kevin, if you could clarify again, the answer there really is all of the above, isn't it? Even if you don't have pressure issues, if you've got flow issues, you still need to do some sample conditioning. If all you've got is a temperature problem, but pressure and flow are great, still want to be looking at sample conditioning. Is that correct?
Correct. Actually, a deviation on any one of those 3 points, temperature, pressure, or flow, would require that some type of sample conditioning be done.
Okay, thank you.
Okay, we'll continue on here. So when we do the sample conditioning, the order of process that we do the control with is important. So the P&ID here on the right actually shows the configuration of cooling, pressure regulation, and flow regulation in the order that the process happens. So the first thing we do is we reduce the temperature. And you can see there the sample cooler is highlighted or cleared. So we convert, if we're in a steam mode, we convert into a liquid so that we can handle the next step. And that would be reducing the pressure. In this case, we have a high pressure regulating valve. If this was a low pressure application, we would have a low pressure valve in that position. And then finally, after we've dropped the temperature and the pressure to the ranges that we need, then we need to regulate the flow so that we can maintain consistent performance to the analyzers. So cooling must occur before making the pressure adjustment. Main reason for that is if you try to reduce pressure in a steam sample, it's very costly and very difficult to do. The valving becomes extremely more difficult. So we want to go ahead and get to the liquid phase first before we do the pressure adjustments. Second thing is, we look at whether or not we need a temperature shutoff valve. This is basically a safety device so that if we were to lose cooling water to the cooler and the sample converted back to steam, the last thing we would want to do is have that steam go into the instrument and basically destroy it. So we design with that in mind. Also, many measurements are temperature dependent. A lot of people talk about the accuracy being the key point that they have. This is one of the potential problems. Different measurements are very dependent upon temperature. Silica, for example, even if the sample is cool, can actually be too cool to where the colorimetric measurement is not able to complete the chemistry because the reaction times have changed dramatically due to the lower temperatures. Conversely, if we have high temperatures, they can actually damage the instruments and shorten the probe lifespans. Any of the ion-specific measurements, pH, sodium, for example, at higher temperatures, the probe itself, the glass, actually becomes degraded at those temperatures, and the potassium chloride or gel fill inside the probes thins out and will pour out at a higher rate, thus reducing the lifespan of that probe dramatically. And then temperature compensation versus solution compensation. I know many of you have heard the terms temperature compensation. It's not one that a lot of people are fully aware of what it means. The temperature compensation is actually the mechanical correction for temperature's impact on the hardware. So an ion-specific electrode, mechanically it actually shifts at different temperature and will not generate the same millivolt response to the ion that it will at other temperatures. So the analyzers actually correct for that in accounting for that mechanical shift. Solution compensation is one that not everybody is aware of, or a lot of the instrumentation historically has not had the capability of solution compensation. And this actually accounts for the changes in the ionic species in the fluids at the different temperatures. As we heat a sample up, the ions move at a quicker rate. And the probes or the measurement can actually overcount or overestimate the amount of that ionic species. At lower temperature, the exact opposite happens. The ions slow their movement, and the analyzers can underreport what is actually in the solution. So temperature correction or compensation with solution compensation is critical to the accuracy of the measurement. So how do we control the temperature? Well, at Swan, we use high efficiency counterflow design sample coolers. They are an all stainless steel construction with a single gasketed design, reducing the potential points of failure, as well as reducing maintenance requirements. All of the units are 100% hydrostatically tested on both the shell and the tube side. And we have a variety of shell and tube materials available. So if you have a saltwater application, high chlorine, or extremely high temperatures, we have different materials for the tube and the shell to account for those requirements. On the pressure side, we make sure that our valve is sized appropriately for the system pressure required. This is a picture of a high pressure valve, but like I said, at lower pressures, we need to make sure that that valve is selected for the appropriate pressure drop, as well as the CV across the valve, so that we don't take too much pressure away from the analysis. We design around the EPRI and ASME recommendations, and we use rod and tube devices for high pressure applications. All the wetted parts are stainless steel, and the high pressure units are cleanable in place, so there is no disassembly required in order to clean the valve, even in high pressure applications. It also gives us a laminar flow, which gives us much greater control across the wide variety of pressure drops that we design for. And it eliminates erosion and plugging. So The third thing that we need to address is the flow. A lot of processes now, especially in the power industries, are now dealing with sliding load or peaking processes, meaning that the pressure that's coming in to the analyzers or from the process is changing, and it may change dramatically over short periods of time. Same thing in industrial applications. If we're on the downstream side of a piston pump, for example, every time that pump fires, we get a pulse of pressure. So we design with those sliding loads in mind. So we utilize a back pressure regulation instead of the old fore pressure regulation. Reason being, a fore pressure regulator is basically a reduction orifice. So if the upstream pressure changes, either higher or lower, the downstream pressure will shift as well. With a back pressure regulation device, we actually maintain the upstream pressure at the desired set point, and we actually take the excess pressures to waste, so that as the load shifts, the only thing that changes is the amount of water going to waste rather than the flow to the analyzer. We utilize a fixed pressure control or a fixed set point, thus eliminating any of the plant's requirement to go ahead and dial that pressure in or make sure that nobody has adjusted it. Ours are all fixed pressure. And it provides a constant pressure over a wide flow range. So even if we have dramatic changes in the inlet pressure, the device can handle it while still maintaining that constant output. It also protects the system from overpressurization. All of the back pressure devices that Swan uses are also considered to be a true relief valve. So even in requirements where the ASME requirements state that we need to have a relief valve, the back pressure device that we use meets both requirements. Has a large orifice, so we don't have problems with pluggage or things sticking inside and keeping the unit from operating. It will not wire draw or erode. So when we control the flow, we're looking to also maintain a velocity of 5 to 6 feet per second. And the reason we do this is we want to maintain an equilibrium of the ionic and particulate components. What that means is that what's in the system or in the solution remains in the solution so that we can get a representative sample to the instrument and get that repetitive measurement. Ideally, sample lines in a sample system should be 1/4 inch at the flow rates of 1200 cc's per minute. That provides us the velocity at that 6 feet per second. If we were to use a 3/8 inch tube, we would require 3300 cc's per minute in order to get that same velocity. Because most of the samples that we're running, we're only going to need, 300 to 600 cc's for the analysis being done. There's no reason to waste all of that additional water, so we typically design for 1/4 inch. Also, sample tubes need to be of an inert material, meaning stainless steel. We don't want to use copper. We want to be careful about some of the poly tubes. Anything that's going to leach or provide some of the material from the tubing to get into the sample and skew our readings would be something that we want to avoid and stay away from. As the tube diameter increases, greater flow is required. So we want to maintain equilibrium. What we're seeing here is if we were in deposition mode or a reduced velocity, A lot of the dissolved and undissolved species in the water will actually fall out of suspension and deposit on the tube, thus getting us a unrepresentative sample to the analyzer. If we are at a higher flow or higher velocity, then we get into the erosion or entrainment, where we're actually taking and scraping material off of the tube and carrying it with us. Again, bringing more material than what was in the sample originally to the analyzer, again, skewing the measurements. So we try to make sure that we're at that 5 to 6 feet per second or equilibrium state, so that what's in the sample remains in the sample, what's on the tube remains on the tube. This graph here is showing basically the different modes, deposition versus equilibrium. So at the lower velocities here, you can see we're actually depositing material and we're in that deposition state. If we get higher velocities, we then fall into that erosion state. We're actually carrying part of the tube and part of the deposits from that sample line to the analyzer and giving us a non-representative sample. So again, we're looking for that 5 to 6 feet per second equilibrium. And that actually, as you can see on the graph here, comes together for both horizontal and vertical tubes at that 5 to 6 feet per second. So that's kind of the sweet spot that we designed for. This is showing a graph of how long it takes for us to reach that equilibrium state. And it takes considerable amount of time to reach those stable points. So at low velocities, we never hit that equilibrium. We just can't. We're just dropping material down the tube. If we get at higher velocities, again, we start transporting more material than what was in the sample. So again, we're looking for that 6 feet per second, where we're transporting the equal amount of what was in the sample to the analyzer. You can see here, though, on this graph that it can take, a month to 2 months of stable flow before you reach that equilibrium point and can transport without any carryover or influx from the sample line itself. So the other thing we need to be cognizant of is the sample lag time. So we start out here with the 1/4-inch tube. At 500 cc's, you can see, one, our velocity is too low. We're in that deposition state. And two, we take 6.5 minutes to transport that sample 1,000 feet. At the 1,200 cc's, we're now at the velocity we want, and our transport time is 2.5 minutes or 2.8 minutes. If we were to use a larger tube, you can see at the 500 cc's, we're well below the velocity we want. We're at 18.7 minutes. At 1,200 cc's, we're still below the velocity, and we're at 7.5 minutes. It's not until we get to that 3,300 cc's that we get the right velocity and we get our lag time back in line with what we're looking for. Again, that 3,300 cc's is considerably more water than what we need, so there's no advantage to running those larger tubes. And if we control at the correct velocity, you will have the same potential of pluggage in tubing in a 1/4-inch tube as you would in a 3/8 if we maintain that velocity of 5 to 6 feet per second. Some of the other things we take into account when we're designing these systems is, do we need filters? Do we need to protect the conditioning elements or the analyzers from some of the material that we may be transporting? With that, we're looking to protect the instrument, but we need to be sure that we're doing it without changing the ions of interest. So in this case here, we have pictures of what we call a mag trap. It uses a magnetic field to go ahead and remove iron particles, which can be harmful to the analyzers, but yet it does not change or adjust any of the ion species that we're actually trying to measure. The other thing we look at is service and maintenance, because even a well-designed system is going to need maintenance and care. Calibrations need to be done, the analyzers need to be cared for, and those are part of the design considerations. So some of the Swan designs, one, we can provide complete sample conditioning and analysis solutions for basically any type of a water process that requires analysis. We provide wall racks. We can do freestanding floor racks. We also offer turnkey startup and service on any of the racks or processes that you have. We also do applications in a variety of markets, from drinking water plants to industrial treatment to conventional power and nuclear facilities. We have ideal solutions for distribution monitoring. As again, the picture shows here one of our packages. We also can do outdoor enclosures for a variety of environments. So whether you have an analyzer that needs to be out in the sun and snow and wind, or you have a dirty indoor environment, or if it's an explosion-proof requirement, we can provide custom solutions for any of those applications. We can also integrate our solutions into your existing equipment. So if you have an analysis panel and you need to add some things to it, we can come in and do those integrations for you as well. And we custom design for any of your individual requirements. You tell us what you want, we'll tell you whether or not it can be done and how we can accommodate it. We also have worldwide experience. Swan Analytical is a worldwide company. We have engineering offices throughout the world, Europe, Asia, South America. Our headquarters is in Switzerland, and all of the engineering groups report back to Switzerland. So whether we've run across some experience in Asia or in Europe, every one of the engineering groups worldwide is aware of any challenges or how we came up with solutions to accommodate those needs. With that, we have a full range of expertise and support offerings. We also are offering site assessments and analysis. So if you have a process that you know you're struggling with, but you don't know exactly where to go, what to do, feel free to give us a call. We're more than happy to come out and take a look at your process and make recommendations as to how to correct and remedy some of the issues that you're dealing with. Again, the important conditioning parameters that we need to address in any system are temperature, making sure that we reduce and control so that we can get viable measurements and prevent damage to the analyzers. Pressure, we need to make sure that we've got the pressure dropped down to workable levels. And we want to make sure that in the flow characteristics, we're one, making sure that the velocity is correct to maintain that equilibrium, and that we can ensure the sample integrity and provide repeatable measurements. Everybody, again, mentioned earlier that one of the big concerns that they have is the accuracy of the instrumentation. By taking care of the temperature, the pressure, and guaranteeing a stable flow with the constituents of the sample being carried from the process to the analyzer will allow you to go ahead and get those repeatable, accurate measurements. So in conclusion, a properly designed sample system transports and conditions the samples from the point of extraction to the analysis points without altering the characteristics of interest. For more information on sampling from Swan, feel free to contact our office at the number listed. You're always welcome to send me an email directly, and that's my email, or give me a call. My cell phone number is 920-400-0028, or feel free to contact your local Swan sales associate, and they can put you in touch with myself or get the information so that we know how to proceed from there. I would like to thank you all for attending. At this point, I think, Dom, did we get some questions here?
We did, Kevin. First off, thank you very much. It was really good stuff today. So the first question we have was relating back to slide 18, where we were talking about velocity versus deposition. And Nancy asks, do we have a reference for that? I know that when we were going through the deck, you mentioned that was a slide you've been familiar with for years and years. Where does that originate from again?
That was testing that was actually done, and this graph is actually pulled directly from the EPRI reports. What they did was they actually injected a known volume of material into a fluid at a specific velocity, and then they actually measured the weight of the deposition through the section of the tube. So those were all tests that were done by EPRI. I mean, it's been quite a while. I think those were done back in the mid-70s.
Okay, thank you very much. I've got Randy here with me as well, and Randy had pulled in a couple other questions as well. Randy, could you help us out there?
Yes, Kevin. At what process sample temperature would you recommend installing temperature shutoff valves on the sample line?
Basically, to me, anytime I get over or get up into the 110 and above degrees Fahrenheit, typically the set point that we utilize for the TSV is 120 degrees Fahrenheit. So really, anytime we get above that, you can start seeing if we did not cool the sample or correct the temperature via temperature compensation, we would want to make sure that we were protecting the instrumentation. So anytime we get up into the points where we're dealing with extremely warm water, or especially if we're in the steam samples, then it would definitely be a recommendation that we have the thermal shutoff valve.
Thanks, Kevin. I've got another question here from Robert. He was asking about the slide on isokinetic sampling, and just asking for a little bit more comment on the details on how to do it correctly. And are there sample streams that are more critical when we're talking about that isokinetic sampling requirement?
Yes, and I'm trying to pull up the slide here, but either way, isokinetic sampling is typically done in saturated steam samples. The reason we do that is the flow dynamics of steam inside of the tube actually, as you get away from the center of the tube towards the wall, because it's a turbulent flow, it's very difficult to get a representative sample unless you actually measure at different points across the entire interior of that steam tube. So isokinetic sampling is typically a method of pulling different points of steam from across that full diameter of the tube. So we get some from the middle, some from the edge, some from the other edge, and everywhere in between. Where it becomes very problematic is when we get into low water content steam, because we're taking a large volume of steam, but there's very little water in it. By the time we condense it, it's hard to get enough water vapor or flow in the liquid stage to actually transport at the correct velocities. So that's one that the designing of that is very difficult. And when it's done wrong, typically it means that you're not getting any sample to the analyzers. I hope that helps. If not, please feel free to give me a call afterwards and we can discuss it further.
Kevin, thank you very much. I have one other question with respect to sample flow regulation. Do you recommend installing back pressure regulators, flow regulators on all samples?
Short answer is yes. There may be situations where, because of the limited flow that's available, I may not have the excess pressure that I need to do a back pressure regulation. But for 99% of the applications, back pressure regulation device would be my first recommendation.
Okay, thank you, Kevin. I think that just about wraps it up. I don't see any more questions coming in. I do want to do two last bits of housekeeping. I forgot to mention this at the start, but if you look at your GoToWebinar control panel, you'll see that there's a section there called Handouts, and then you'll find a single-page flyer that gives you an overview of our offering in this area. If you're looking for a copy of the presentation, I will say that this will be available as on demand for replay at our Go to Stage page. And finally, that we have a short survey that we're asking you to fill out at the end of this. If you fill that out, I promise you I'll send you off a electronic file copy of this webinar. And with that, if there's no more questions, we'll bring this to a close. I want to thank you again for your time and thank Kevin again for his presentation. We hope to see you on a Swan USA webinar at some point in the future. Have a good day.